Molecular orbital theory of bonding is built on a key insight. Because we're talking about molecules, we should think about the regions of space in which electrons could be found as molecular, not associated with any particular atom or any particular atomic orbital. An important tenet of molecular orbital theory suggests that the number of molecular orbitals associated with bonding is the same as the number of atomic p orbitals that are overlapping to cause those molecular orbitals. And it's also important to note that the energetics of those molecular orbitals will not necessarily be the same as the p orbitals. Some of the molecular orbitals will be lower in energy. Electrons in those orbitals will be more stable. Those orbitals are called bonding molecular orbitals. Some of the molecular orbitals will be the same energy as the p orbitals. They're called non-bonding. And still other molecular orbitals will be higher in energy than the atomic p orbitals. These guys are called antibonding molecular orbitals because they're a higher energy, and if electrons are in them, they actually destabilize the molecule. 1,3-butadiene has 4 atomic p orbitals on adjacent carbons. When they line up parallel with each other, they all interact, so they'll make a 4-carbon pi system. But our MO theory says these will be 4 molecular orbitals. The energetics of these molecular orbitals can be depicted here. We start with 4 p orbitals, all the same energy, having some arbitrary energy on this energy scale. And notice that the 4 molecular orbitals have 2 that are stabilized and 2 that are destabilized. Pi 1 and pi 2 are bonding orbitals, and pi 3 and pi 4 are antibonding orbitals that are designated with an asterisk. Now each one of these p orbitals in this 1,3-butadiene brings an electron with it, so we have 4 electrons in this pi system. That's why we wrote the 2 lines for the double bonds here and here. So we need to put 4 electrons in these molecular orbitals. And in fact, notice this, that the bonding orbitals can accommodate all 4 electrons. And furthermore, notice that all 4 electrons are in orbitals that are more stable than the p orbitals. So this molecular orbital system is stabilized energetically. This explains the stability of alkenes. The other 2 orbitals, pi 3, which is a pi star orbital, and an antibonding pi 4, don't have any electrons in them. Now, if we'd like to get a picture of what these orbitals actually look like with respect to the molecule, we can draw that out. We can start by noticing that there are 4 ways to arrange these p orbitals that are adjacent to each other. For the bottom one, all 4 orbitals are in phase. For the next higher one in energy, there are only 2 orbitals that are adjacent that are not in phase. For the next one up, there are 2 pairs of adjacent orbitals that are not in phase. That is, to go from this adjacent orbital to this one, you would have to go down. But these 2 are in phase, these 2 are not. And in the 4th one, none of the adjacent p orbitals are in phase. Having noticed that we have this relationship, all in phase, 1 break, 2 breaks, and 3 breaks, we actually say that these arrangements have 0, 1, 2, and 3 nodes. So this term defines how many times we find adjacent p orbitals as we go from left to right that are not in phase. And the more nodes we have, the less stable the orbital is. You'll always find that the most stable molecular orbital is one that has all of the interacting p orbitals in phase. The next one up will have 1 node, the next one up will have 2 nodes, and the next one up will have 3 nodes. Now the actual molecular picture looks like this for the lowest energy molecular orbital. Over the whole length of the pi system, we see a single orbital. It can contain 2 electrons. One portion of that orbital is below the plane, the other portion is above the plane. They're different phases. The higher energy bonding molecular orbital looks a little different. There's a node between these 2 carbons. So now we see that there are 4, not 2, but 4 distinct regions in space for this single molecular orbital. And the probability for finding an electron is defined by the spaces I've shown here. So you can think of this really, can't you, as like 2 double bonds? And it's stabilizing. when we have electron density in there because these electrons are all being shared between carbons. Now let's look at the picture for the first antibonding orbital, the next energy up. Now there are two nodes. There are only two adjacent atoms that share electron density. There are 6 regions in space where the electrons may be found in this single molecular orbital. Remember, this is still one molecular orbital. And the regions in space don't contribute to a whole lot of bonding because there's not a whole lot of electron sharing among these carbons. And the highest energy orbital is even worse. There are 8 different regions where you might find electron density if an electron were in that orbit, but none of it involves sharing with other carbons. So it is the highest energy, it is anti-bonding, it is destabilizing. When we look at them all, you see a picture where there's the most electron density sharing among the 4 carbons in the lowest energy. And as we move up in energy from another bonding to antibonding to further to antibonding, we have less and less electron density sharing. So let's look at a triene where we have 6 adjacent p orbitals. I've lined up the 6 atomic orbitals here at some arbitrary energy value. I put 6 dashes to represent the energies of these orbitals. And then I put 6 dashes to represent the energetics of the 6 resulting molecular orbitals. 6 p orbitals interacting result in 6 molecular orbitals. 3 of these are bonding, more stable, lower energy, and 3 of these are antibonding, less stable, higher energy. And you know that each one of these p orbitals brings an electron with it, so there are 6 electrons that we have to fit in these 6 molecular orbitals. And look, again, they all go in the bonding orbitals, more stable than the p orbitals that they originally were in. So this is a stable system. All of the antibonding orbitals are empty. All of the bonding orbitals are full. And then we draw out the actual picture where electron density is in the molecule, drawing in 6 carbons held together by sigma bonds, and then showing the electron density of the pi bonds. We see that for the most stable pi 1 orbital, there are 2 areas where we might find electron density. Both are shared among all of the carbon atoms, one above the plane of the pi system and one below the plane of the pi system. Energetically, the next highest orbital will be a bonding orbital that should have 1 node. And there it is. That results in 4 regions in space where we might find electrons, with the phases as I've shown them here. When we go up another energy level, we still have a bonding orbital. There are 2 nodes, results in 6 regions in space, but in every case, those regions in space are sharing electron density between carbons, so they contribute to bonding. In contrast, when we go up energetically another level, we have an anti-bonding orbital because now we have 3 nodes. We have less sharing of electron density between carbons than we would if we just had the p orbitals themselves next to each other. Electron density in this orbital is destabilizing. We add a node when we go up another energy level, and there's even less electron sharing, and it's even less stable in the highest antibonding orbital. There are 5 nodes, and there's no sharing of electron density between carbons at all. So again, here's our picture. The most stable orbital has the most sharing of electron density. As we increase in energy, there are more nodes, breaks in sharing. And as we go to antibonding orbitals, there's so little sharing of electrons between carbons that the electron density in there is actually destabilizing.